You're watching PowerNation.
From simple hand tools and an afternoon in your garage,
To a machine shop full of industrial-grade equipment,
there's plenty of ways to help your engine run its best.
today on Engine Power, we'll show you how.
Welcome to Engine Power. We recently took you behind the scenes to show you all the prep work that goes into a block before we even get it on camera. Now, we got a lot of great stuff done, but there's still more to do. If you haven't seen what we've done so far, check this out.
We started with a remanufactured 4.3-liter Chevy V6, which we tore down, probably with some future upgrades in mind. We measured the deck clearance at TDC, which was 39.5 thousandths in the hole. Not great for compression, but the factory hydraulic roller camshaft gives us good versatility for making more horsepower down the road.
With the engine down to a bare block, we chased all the threads to remove any debris. We reinstalled the main caps, torqued them to spec, and checked the main housing bore size. Ours were well within spec, so we moved on to the cylinder bores, which came in 20 thousandths over. Finally, we deburred the engine to remove sharp edges and chamfered the bolt holes to protect the top of the threads.
That is a good start, but there is always more to do, so we're going to show you a little bit more tech on this block right here. We're going to show you some oiling system mods, do a little bit of cylinder head work, and show how to prep a block for better pistons. And with that being said, let's get started.
We'll start by removing all of the threaded oil gallery plugs. That allows us to knock out the press fit plugs using a metal rod and a hammer.
To make sure no debris gets stuck behind them, we'll also knock out the cam bearings. The oil filter adapter and internal filter bypass valve are removed next. Threading and plugging the bypass valve hole ensures that oil is always filtered before it enters the engine. We'll also thread the front oil galleries for pipe plugs. This is a more secure way to seal the galleries compared to the press-in plug. While we've got the tap set out, we'll tap the water pump bypass hole in the front of the block. Being able to plug this allows us to use an electric water pump in the future. The new threads are then cleaned with some Berryman Products brake parts cleaner.
Now that we've got that done, we're going to be moving on to some other oiling mods. Now what we're going to be doing is basically going through the oiling passages and trying to eliminate any sharp edges. Sharp edges can create turbulence and reduce flow, which is bad. Now this is universal for pretty much any engine, but on our V6, since it's similar to a small block Chevy, we're going to be smoothing out places like where the oil returns from the filter and goes back in the engine. We're also going to be trying to clean up any drainage ports so that the oil can get back to the pan faster.
In addition to what Frankie is doing, I'll be working on the rear main cap where the oil pump bolts down to it. Oil flows through the pump into the cap, and it has a very sharp edge, and it definitely needs some attention. I'll be looking at the oil pump itself to see if it needs any work as well. Typically it does. Now this is very simple to do, but you can get yourself into a lot of trouble if you hurry, and you can mess something up very easily. So take your time, take small bites, and you can do it yourself.
Using a ball carbide, the sharp edges are broken and gradually rounded into a radius. After the carbide does the work, everything gets smoothed out with a cartridge roll. The finished result allows oil to flow unrestricted into the block. Now that the main cap's done, we're going to go ahead and just follow the flow of oil. So it comes out of the cap, goes into the block, and then comes over and goes into our oil filter area. Then after it goes through the oil filter, it's going to go back down through this hole and back into the engine. So we're just going to go through, clean up any sharp edges, and try and turn them into nice smooth radiuses. The same ball carbide used on the cap allows us to get into tight spaces. Using light pressure and letting the carbide do the work is crucial. Going through different holes and using a variety of bits can make the job easier. We'll just blow out the debris for now, and when all the work is done, the engine will get a deep, thorough cleaning.
We're just removing the minimal amount of material to round off the sharp edge, and nothing more. Once again, a cartridge roll provides a smooth finish. Even the places that are harder to see still need just as much attention, like this port, which sends filtered oil directly into the block. Another area on any block that could always use work is the oil return. Ours has some jagged edges left over from the casting process, which will impede the oil flow. That's much better. To really make your engine go, first you gotta make it flow. Up next, we'll show you how to improve airflow on your cylinder heads.
Hey guys, I'm hanging out with Team Summit NHRA funny car driver Tim Wilkerson. Tim, today's subject is something that I think can get a lot of engine builders in trouble.
Well, you're absolutely right, Frankie. We're talking about the difference between threading or cleaning a tapped or threaded hole.
Okay, so what's the difference and what's the correct tooling to use in each situation?
Well, basically, I use in layman's terms, if you are going to use a tap, you're making a new hole. If you're trying to clean a hole that has a damaged thread or some debris in it, you want to use a cleanup tool.
Yeah, I agree with that, Tim. I think sometimes guys are too quick to grab a machine tap for something important like a head bolt hole.
Well, you're absolutely right. What happens is you end up running that machine tap through there. It actually distorts the thread. When you put the bolt in there, you lose clamp, doesn't have the correct torque.
So for something like that, you'd want to use a thread restorer kit like this.
Exactly. That's your best effort on either the thread of a bolt or the thread in the hole.
So the next time you need to fix a threaded hole, you need to use the right tool for the job.
We're moving on to show some cylinder head work. For demonstration purposes, we have our Chevy 4.3 liter V6 head up on the Superflow SF750. Airflow through an engine is what makes horsepower, and we can measure that very accurately. So we're going to get some baseline numbers on this head. This head is just like its V8 counterpart. It has a 1.940 intake valve, 1.500 exhaust valve, and it's a TBI swirl port design. After finding out our baseline numbers, we're going to take the head off and make some small changes to it and see if we pick up flow. Again, this is another area where if you just get in there and start grinding, you can do more harm than good. So we're going to show you how to keep yourself out of trouble. We'll start off by flowing the intake in 100 thousandths increments up to 600 thousandths valve lift. As expected, we weren't expecting much. At peak lift, the intake port flows a mediocre 198 CFM. Switching over to the exhaust, we'll repeat the process. The lackluster port levels out at 133 CFM. We are not going to get too crazy, but we will focus on these areas here where the valve job was cut. This is the bottom bowl cut. We're going to blend that in. And there's two humps on the short side radius of both of these ports. We're just going to go in and clean those up, but not make anything bigger. This is real easy work, but just take your time and go in small increments and check your work continually.
Since it's really messy, porting cast iron is not a lot of fun, but it's a great way to get yourself accustomed to grinding. Compared to aluminum, material gets removed at a slower rate. One important note, be very careful around the valve seat. If you accidentally touch it with the grinder, you'll have to have the valve job redone. A couple of different carbides are used to reach tighter areas of the port. We'll switch to a cartridge roll to put the final finish on the bolt.
We'll give the same treatment to the exhaust and we'll get it back on the flow bench. We'll run the same test to see if we've made any improvements. Both the intake and exhaust perked up nicely from our baseline numbers. On the intake side, we gained 17 CFM at peak lift, but all points of measurement showed an increase. We had an average gain of 13.33 CFM.
The exhaust was even better. At peak lift, we got a solid 33 CFM increase, and our average gain was an identical 13.33 CFM.
These are some nice little gains for a minimal amount of work. I spent about 20 minutes on each port. I didn't make them any bigger, I just smoothed them out and knocked down the rough edges. Keep in mind, the runner was not touched. That's one area where if you start reshaping things and making it bigger, you can cause all types of problems. This is something that you can do at home that will definitely pick you up some horsepower.
Up next, inside the cylinder bore is where power is made. So setting them up correctly is crucial for peak performance.
We have some happy little plug wires. Let's, oh, I think he wants to go right there. Let's put a sibling right next to him. That's nice. Hello, I'm Pat Topolinski, and I'd love to welcome you to the joy of engine building. You know, growing up in northern Michigan as a small boy, I would tune into public television and watch this amazing man paint these beautiful pictures, and it was so inspiring, and it was fun to listen to, the way the brush crunched against the canvas. I decided I would love to do the same thing one day. And after years of practice and hard work, I came to the realization that I have absolutely zero talent for painting. So I did the next best thing, become a professional race engine builder. Race engine building and painting have many parallels, like there are no mistakes, they're just happy accidents. Actually, that's not true at all. In engine building, if you make a mistake, it usually causes catastrophic engine failure. And then you end up with a pile of broken parts and even more broken dreams.
What are you doing in here?
I'm just living in the 80s, man.
Come on, man. We got work to do.
All right. Next on our list of tech to show you is getting a block ready to get honed. Now, you usually see us hone blocks where we get them in and get them out. This time we're gonna go a little bit behind the scenes and show you what it takes to prep a block to go in the hone and get done right. And the big part of that is the fasteners.
When you're bolting down your cylinder head, you can either use studs or you can use bolts, and it really doesn't matter. But when you're trying to torque plate hone an engine, you're trying to recreate the distortion that happens during final assembly. So it's always the best idea to use the fasteners you're going to use when you actually put the head on. If we were to build this 4.3, we would probably put some studs in it. So that's what we're going to do here. We'll get our studs in, and then we can torque our torque plate on, and we might even show you the distortion that happens.
Just as important is having the mains on to recreate lower cylinder distortion. So we'll put the main caps on and torque them to spec, and we'll probably show you what that does to the cylinder when that's all done.
The mains are torqued to spec at 65 pound-feet. Even though it's designed for a small block V8, the ICT torque plate works fine with our V6. The bore spacing and bolt pattern are identical on both engines. We'll apply some ARP Ultra Torque Lube and torque the studs in 3 stages to ARP's specification of 80 pound-feet. We'll then take multiple cylinder bore measurements at 3 depths inside the cylinder to document the distortions in the bore. We've gone ahead and measured our bore before and after putting on our torque plate and mains, and this is kind of a good way to give you a visual of what's actually happening. You can see some pretty big changes going on just by the numbers, but it kind of depends on where you measure in the bore and how close you are to a fastener. Like here, we can see that it's grown almost 13 10,000ths in just one spot. So now that we have our torque plate and mains bolted on, when we hone it, it'll be round and straight for our final assembly.
Our block is now installed in our SV15. Now, just like the torque plate on the top and torquing the mains on the bottom, the mechanism that holds the block in the hone, if you over torque that, you can distort the cylinders as well, so you gotta be careful. Now we're gonna go over a few things that we're gonna set up on the machine itself to make sure we get the right hone, and it's gonna deal with size and the actual travel of the head. So we're gonna go to the screen. We have to plug in a few parameters to make sure the machine understands what we're doing. First is going to be bore diameter, and on this block that will be 4-inch 30,000ths. Next, the bore length. That is the physical length of the cylinder itself. On this particular engine, like its 350 V8 counterpart, it is 500. The stone length is a given because we can just measure that, and they're 3-inch. Overstroke, that is how much the stone comes out of the top, and the overstroke on the bottom is how much it comes out of the bottom. So 3/8 of an inch on each one. And our ratchet setting is a physical setting on the machine itself to how much it expands the stones every cycle, and we're going to set that at 1. The next thing we'll set is spindle speed and the stroke, and that determines our crosshatch angle. On a block like this, we are going to set it at about 36 to 38 degrees. Right now, as it sits, we have a roughing spindle speed of 190 and a rough stroke speed of 80, and that puts our crosshatch angle at 38 degrees. Cut that in half because the spindle spins half as fast on the finishing side, it still ends up at 38. I will both rough and finish the bore at the same crosshatch angle. That way the bore stays consistent. Those parameters are already in, so we are all set to go. Up next, we prep our block for bigger pistons and measure the results down to the millionth of an inch. To get to our 4030 final bore size, we have to take roughly 10 thousandths out. We will be using diamond abrasives. First, we'll start off with a 220 grit stone and then finish with a 600. This machine has no problem taking that amount of material out. We could even take more out if we wanted to. With the diamonds, it keeps the cylinder very straight and very round. So we're going to raise our cabinet and get going. First thing we're going to do is we're going to turn the machine on with no oil in it. We're going to be able to hear that cylinder. Run it slow through the travel to make sure it doesn't hit anything. And hear that? Right now the cylinder is kind of hunting because the machine will actually detect the tight spots. And that's what it's doing right now, and it auto dwells. Boy, she's really out of round. Holy moly. You really don't want to put an excessive amount of pressure on something like that initially because it is so far out of round, it'll start doing some very bad things with chatter. So we're just trying to sneak up on it. You can tell when it was first going how it was really notchy sounding. It's starting to settle back down. We're just trying to get it straight before we remove the bulk of the material. And now we're going to go till our cylinder straightens up as much as it can. Then we're going to check it to see how our progress is. We're going to hone it within about 1/1000th of its final size. Taking roughly 4 thousandths out of the board. It's a little tighter at the bottom, but that's okay. The important part now is the cylinder is round and straight. It took 4 thousandths to do it, but we still have 6 thousandths to go to get to our final size. But now we can take out the rest of the material and not have any more problems. We'll get it within about 1/1000th of our final bore size, and then we'll switch stones. That sounds way better. Cylinder sealing is a combination of a bunch of different factors, but the main one is how accurate the cylinder is, how round it is, and how straight it is. We are just under 1/1000th to go to get to final size, so the next thing we have to do is switch our stones. We're going from our 220 grit diamond to a 600 grit diamond, but before we do that, we have to get these cleaned off for the next time. So what I'm going to do is use some Berryman brake parts cleaner to hose them off. I really like using the Berryman parts cleaner for several different reasons. 1, it cleans off all of our oil very well. 2, it leaves no residue. And 3, it is fast drying. So we're just going to put our popcorn can over it here, and we're going to give it a spray. Look at that, it's already starting to evaporate off. Berryman brake parts cleaner is very versatile. I don't know if it was specifically designed for cleaning off honing oil off a diamond head, but it works awfully well for that. For finish honing, we'll replace the 220 grit abrasives with 600 grit abrasive. A dressing stone makes sure those abrasives are clean before we get started. Any residue left behind is removed with more Berryman brake parts cleaner. This engine block is pretty soft, so it doesn't take long at all to remove the final 1/1000th of material and check our work. Oh, baby. I'll take that. With the cylinder to size, now it's time to check its surface finish. Just because it's been honed doesn't mean it has the proper surface finish for the ring pack or our application. So we are going to measure it with a profilometer. A profilometer has a sapphire stylus that drags across the cylinder and measures very accurately, and it's displayed on our screen. So we're going to check to see what it is. The stylus measures in millionths of an inch and creates a detailed profile of the cylinder's finish. It's securely mounted in the bore because the instrument has to remain completely still during measurement. Our numbers look spot on for the type of ring we will be using in this build.
We've almost wrapped up our 4.3 liter V6 prep, and if you put this much time and effort into an engine build, you're definitely going to want to use quality components during the final assembly, and for that we choose Duralast. We've used Duralast components quite a bit before, and they've taken a bunch of abuse on the dyno. That's because Duralast manufactures their parts to have an OE quality or better. Their sensors and vehicle electronics are manufactured brand new, but they're designed to fit and function better than their OE counterparts. Things like starters, alternators, and water pumps are available new or remanufactured, where Duralast dives in and fixes some of the OE defects and replaces all of the critical wear items with brand new ones. Then components are triple tested throughout the assembly process to make sure that they meet or exceed OE specifications. If you're interested in anything else that Duralast offers, you can go to duralastparts.com.
For more information on anything you've seen today, check out PowerNationTV.com.